Welcome back. Let's now continue with implementing a reinforcement learning algorithm that would adaptively tune the PID constants based on the system states. As a reminder, don't forget to enroll in my free Udemy tutorial, Vehicle Suspension Control 4, PID Tuning with AI, TD3. You will get the code files and video explanations if you enroll in that tutorial. Also, note that the free coupons that I offer for that, they have limitations in terms of time and the number of enrollments. However, don't worry, I will be renewing them periodically. In the last video, we left off with this blueprint, which was designed to train both the critic and the actor neural networks. But before I ended that video, I mentioned that there is a problem with this logic. When you calculate your target Q value and subsequently the error, in order to get this error to 0, you would ideally want the target Q value for given state action pairs to be constant for some time, because that would allow the current Q value for that specific state action pair to converge on the target value. So this here is the time axis, but the idea is that during this time period, we have the same state action pair here, 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 and also here. In other words, as you run your simulation, then of course, in between these instances, you have other states and actions, but then, after some time, when you are in this instance, you would return to the same state action pair that you had in this instance. And you would ideally want the target Q values to be constant at these time instances for this specific state action pair, because then it's easier for the algorithm to drive this error to 0. The problem, however, is that the target Q value also directly depends on the critic. If you are at this instance, and after applying the gradient descent algorithm, you adjust this weight vector in the critic, then since now the weights are different, the next time you have the same state action pair, at this instance, this target Q value will not be here. It will be something else, because the weights in the critic are different, which means that when you pass the same state action pair through the network again, you will obviously get something else for this guy. Therefore, when you have this structure where the critic neural network directly influences the target Q value, you will not have constant reference points allowing your current Q value to conveniently converge on the target value. That makes learning difficult. It can even make it unstable. It's as if this guy constantly tries to catch this guy, but then this target value always jumps away from under your nose. And that might make the error grow bigger and bigger, and you never have any kind of convergence. The solution for this problem is the following. This here is your NN1, which is your actor. It takes in the state vector. It outputs an action vector. In addition to that, tiny noise is added to it. This by itself does not solve the problem we have just discussed. It's an additional feature that is done in these types of algorithms because it helps with learning. I'm going to call this action vector that also contains the noise action vector star. We then have the critic network that takes in this noisy action vector, and it also takes in the state vector. So far, everything is the same, except that now we've added the noise to the action vector, which we denoted with AK star. This will then output the current Q value for this state action pair, where the action vector also includes the tiny noise that is added to it. That action enters the environment, followed by the environment giving you this immediate reward. And let me also complete the loop here. The environment also outputs the states or observations. However, this is where things become different. In order to compute target Q values, a copy of the actor network and the critic network are created. They're called target actor and target critic respectively. Initially, at the beginning of the training, the weights and biases in the actor and the target actor and the critic and the target critic are made the same. Just like before, when you apply the action vector to the environment, before you update the current Q value, you also figure out the new state vector that now you insert in the target actor and not the regular actor, and you also insert it in the target critic, not in the regular critic. This target actor produces an action vector at k plus 1, and for now here we will not add noise to it. Later on in TD3 we will do it, but not here, because right now I'm describing an easier algorithm called DDPG, and according to my research there was no noise added to the action vector that came out of the target actor. This action vector then also enters the target critic. This NN4 network then outputs the Q value for this state action pair, and since it comes out from the target critic, I will put here the subscript T. Just like before, I will multiply a discount factor by it. I will then add this discounted future reward to the immediate reward, and from that I subtract the current Q value, and all that will give me this error that I will try to make zero over time using gradient descent. So what's the purpose of creating these two copies here? Well, here's the reason. Unlike the regular actor and critic networks, the target actor and target critic are updated slower. In fact, they are updated much slower. The weights and biases in these two target networks are updated according to these formulas, where this tau is a very small number. In my code it's 0.005. If you look at the formula, then you can see that every time I update my target networks, I take a tiny portion from their regular counterparts. You have 0.005 here and also here. And then in this term, I have 1 minus tau, which is 0.995. In other words, when I update my target networks, I almost multiply their weights and biases by 1. If 1 minus tau had been 1, then tau would have been 0. In that case, there would have been no contribution from the regular networks to the target ones, and I would simply be multiplying these two vectors by 1, which means that I wouldn't be updating anything here. Even though I'm not doing that, so this is not true, but I'm almost doing that, because this is almost 1. As your regular actor and critic networks get updated, so do the target networks, but at a much slower pace. And this helps solve the earlier problem that we had with not having constant target Q values. Remember that This here was your target Q value. Because of the fact that the weights and biases of the target actor and target critic networks do change, you still don't have constant target values for some state action pair. However, because of the fact that the target actor and target critic are updated much slower compared to regular actor and regular critic networks, they are still relatively constant compared to the current Q value that comes from the regular critic, which still makes it easier for the algorithm to get current Q value closer to the target Q value. The fact that the target networks are updated much slower, it makes it easier for the learning algorithm to drive this error to zero. The target values still change, but compared to regular Q values, they change much slower. And that's why these two additional copies are made. In total, we now have 4 neural networks. As you drive this error to zero, you train the regular critic to better estimate the Q value for some state action pair. When it comes to training the actor, then it's the same like before. You adjust the weights and biases of the regular actor network using gradient descent such that when it takes in a state, you want the regular actor to output an action that maximizes this Q value that comes out of the regular critic network. In general, these types of algorithms are called actor-critic algorithms. It's a family. What I have explained to you here is called Deep Deterministic Policy Gradient, or DDPG. This is one algorithm which is part of this actor-critic family. Another one that I will explain to you next will be TD3, which is also part of this actor-critic family. Finally, once you have trained DDPG enough, when you deploy it on your hardware or in your simulation, you will simply take this regular actor and this is what you will deploy. Your trained actor will take in the states and output the actions based on those states. DDPG showed great promise, but it still had issues, and that's why TD3 was created to address those issues. DDPG is the predecessor of TD3, and so let's talk about it in the next video. Thank you.